All right, to get started with Unit 1, we're going to be looking at mechanisms. And mechanisms are the basic components of most machines, and they usually consist of gears, sprockets, pulley systems, and simple machines. The effective use and understanding of mechanisms has contributed to many different improvements and developments of technology throughout society for hundreds and thousands of years. Engineers and scientists use mechanisms to manipulate speed, distance, force, and function to meet a wide range of design and application requirements. For today's notes, we're going to look at 3 of the 6 simple machines. We're going to focus today on the lever, wheel and axle, and pulley. In engineering, work is a measure of how much force you apply to move an object through the parallel distance the object moves. So I would like you guys to write down this formula to calculate work. It's going to be force times parallel distance. What this essentially means is that in order to do work, an object must move in the direction of forces applied. For example, if you notice the 2 pictures at the bottom, the boy's arms on the left do work when they exert an upward force on the basket and the basket moves upward. Whereas in the second picture, the boy's arms still exert an upward force on the basket, but when the boy walks forward, no work is actually done by his arms. When you are doing work, the force you apply is called the effort force. The weight of the object you are trying to move, or the force that pushes back against your effort, is considered the resistance force. Take a look at this scenario. We have an inclined plane in which we're trying to move a box upward. The product of the effort times the distance, or the work traveled, will be the same regardless of the system's mechanical advantage. Machines never change the amount of work that is done, but they can change the magnitude and the direction of the force. When using a simple machine, such as this inclined plane, like I said, you're actually doing the same amount of work, it just seems easier. In this particular scenario, I'm doing the exact same amount of work to push the box up the inclined plane as it is for me to lift the box up directly. So why is that? It's because a simple machine reduces the amount of effort needed to move something, but you wind up moving it a greater distance to accomplish the same amount of work. So in general, machines can change an input force by changing the distance the force is applied to. As demonstrated in this picture of a woman using a lever to lift a concrete load, by increasing her distance from the pivot in which her input force is applied, it will allow her to increase her output force for lifting the load. Usually, but not always, we want to make our task easier by doing one of 3 things. 1, we could reduce our effort force, which would be our pull, our push, or our twist. Or we could, 2, reduce the distance we apply effort, again, push, pull, or twist. Or 3, change the direction of our effort force. With that said, the purpose of most machines is to make our lives easier. So how do we do that? We use machines as a device that allows for work to be completed easier by multiplying forces or changing the directions of those forces. Simple machines are mechanisms that manipulate magnitude of force and distance. When you think of magnitude, just think magnitude represents the size. So the size of the force, the size of the distance. The 6 simple machines are the lever, wheel and axle, pulley, inclined plane, wedge, and screw. We call these machines simple because they have no or few moving parts. As you can see in the picture, these 6 simple machines have been divided into 2 families, the lever family and the inclined plane family. The lever family consists of the lever, the pulley, and the wheel and axle. The inclined plane family includes the inclined plane, wedge, and screw. Notice that the point in the middle of a fixed pulley is like the fulcrum of a lever. A wheel and axle is a lever that is able to rotate through a complete circle 360 degrees. A wedge is usually made up of 2 inclined planes, and a screw is like the ramp. The width of the thread is the angle of an inclined plane. It is important to note that machines can change the direction of forces. Based off the conservation of energy, no machines can create energy. It can only transfer energy or transform it from one form to another. As output forces are almost always different than the input forces, the output energy can and at best be equal to their input energy if no friction exists. Work that goes into a system is equal to the work that comes out when there is no friction. This would imply that the amount of work put in will be equivalent to the amount of work put out. In reality, however, the output energy will always be less than the input energy because of energy lost due to the friction in the form of heat. Part of designing a machine involves trying to reduce these energy robbers. This is done with ball bearings, lubricants, wheels, low friction materials such as Teflon or graphite powder. One important measure of the amount of help that a machine provides is called mechanical advantage, or MA. The mechanical advantage of a machine tells us how much the machine multiplies our effort force when it is doing work. Machines can have two types of advantage. The first way is that they can change the direction of an input force. The second way is they can multiply the input force. A mathematical model has been developed for mechanical advantage for each simple machine to represent the relationship between the effort force and the resistance force, and at the same time represent the relationship between the distances that each force moves through. If you know the mechanical advantage of a machine and you know the amount of work you want to do, you can predict how much effort you must exert to accomplish the work using the machine. For example, if a mechanical advantage of a machine is 3, the machine increases the effort force we apply by 3 times. An effort force of 10 pounds can now lift a resistance force of 30 pounds. There are 3 ways that we can calculate mechanical advantage. The first way is to consider the ratio of the force of a machine can exert to the amount of force that is put in. So we would calculate this as the ratio of the output force, usually known as our load, our weight or resistance, divided by our input force, usually known as the effort, pull, or push. The second way to calculate mechanical advantage is to calculate the ratio of the magnitude of the resistance and effort force. So we would write this as mechanical advantage is equivalent to the force of my resistance, Fr, divided by my force of my effort, Fe. And then finally, the third way to calculate mechanical advantage is to look at the ratio of distance traveled by the effort and resistance forces. So I would write this as mechanical advantage is equivalent to distance of my effort divided by distance of my resistance. So again, 3 total ways to calculate mechanical advantage. Force out divided by force in, force of my resistance divided by force of my effort, and then distance of my effort divided by distance of my resistance. If you notice in the example below, I just gave you another example of using mechanical advantage. Keep in mind that mechanical advantage has no units, so it is considered a unitless calculation. In the example below, it says if a vehicle has a gear train with a mechanical advantage of 2, for instance, it has twice as much force available to it, enabling it to go up hills that are twice as steep or tow a load that is twice as heavy. As you can see on this slide, the first scenario shows the man lifting a cardboard box 1 meter using 225 newtons of force. In the second scenario, the same man is pushing the cardboard box 3 meters using 75 newtons of force. By using a 3-meter ramp, he was able to make the job 3 times easier. We would say that this inclined plane has a mechanical advantage of 3 to 1, or simply 3. When we're looking at calculating mechanical advantage and understanding it, it's important to consider the ratios. 1 is the magic number. If a mechanical advantage is greater than 1, that implies that proportionally less effort force is required to overcome the resistance force. And also proportionally greater effort distance is required to overcome the resistance force. All right, so there's a trade-off between forces and distance. Less force is going to require a greater distance. If mechanical advantage is less than 1, proportionally greater effort force is required to overcome the resistance force. Proportionally less effort distance is required to overcome the resistance force. So again, greater effort force, or more force, is going to require less of a distance. So again, there's that trade-off. They're indirectly proportional. One goes up, the other goes down. Greater effort, less distance. Less effort, greater distance. So to kind of summarize this, again, mechanical advantage is the measure of change in force magnitude achieved by using a machine. If our mechanical advantage is equivalent to 1, That essentially means that the effort force is equal to the output force. If our mechanical advantage is greater than 1, the effort force is increased by X number of times. If our mechanical advantage is less than 1, the effort force is decreased by a factor of X. The greater the mechanical advantage, the less effort needed to lift the load. So continuing to look at mechanical advantage in depth, if a mechanical advantage is greater than 1, the force has the advantage. The machine will increase the force, but it's going to require you to move a larger distance. So consider this example. A car jack helps by having a large mechanical advantage. However, when you use a car jack, you have to push up and down numerous times in order to increase or push that load. If your mechanical advantage is less than 1, now the distance has the advantage. The machine increases the distance and speed, but it's going to reduce the force. So consider this example. Your bicep muscle contracts a little to move your whole entire forearm. So in general, again, a mechanical advantage of greater than 1, increase the effort distance provides increased output force. A mechanical advantage of less than 1, increased effort force provides increased output distance. So coming back to this example of the inclined plane, a mechanical advantage of 4 to 1 simply tells us what about a mechanism. In terms of the magnitude of the force, effort force magnitude is going to be 4 times less than the magnitude of the resistance force. So that is implying that if I was to push this box up this inclined plane, I would have to use 4 times less the amount of effort than if I was to essentially lift the box directly up. However, the distance that's traveled by the force changes because of me using the inclined plane. I'm going to have to travel 4 times a greater distance than the resistance force would be if I was just to directly lift it up. When we calculate mechanical advantage of a machine, we often assume an ideal world. The machine components are weightless and they work perfectly. They do not bend or wear, and no friction is created between interacting components. This is going to be considered or referred to as ideal mechanical advantage, or IMA for short. IMA ignores all the realities that can cause a machine to lose energy. To calculate IMA, we're simply going to use the effort distance divided by our resistance distance. So IMA is equivalent to dE over dR. It is a theory-based calculation where no friction is taken into account. But because we do not live in an ideal world, we need to know what the real mechanical advantage is so that we can account for and plan for those losses. We refer to this more realistic mechanical advantage as actual mechanical advantage, or AMA. AMA takes into account all of the energy losses in a machine and is defined in terms of the magnitude of the effort force, FE, which is our input, and the actual magnitude of the force that the machine produces, which is our resistance force, FR. To calculate AMA, it's going to be FR, our resistance force, divided by FE, our effort force. Because distances are often easier to measure than input and output forces, especially when you are designing a machine and you can't measure the actual output force, IMA is often used to inform machine design. So looking at our first simple machine, a lever is a rigid bar used to exert a pressure or sustain a weight at one point of its length by the application of a force at a second point and turning on a fulcrum or pivot at a third. There are 3 classes of levers. The first class lever places the fulcrum, the pivot point, between the effort and resistance forces. Effort and resistance forces are applied to the lever arm in the same direction. And it is the only class of lever that can have a mechanical advantage greater than 1 or less than 1. A first-class lever always changes the direction of forces. Examples of first-class levers include seesaws, crowbars, pliers, or scissors. As seen in the picture, you can push gently on a long lever to lift something heavy, but only for a short distance. To move something a long distance, you have to apply a powerful input force on a short lever. So again, referring back to that trade-off of force and distance. So to summarize, the distance of my effort, dE, is equivalent to the distance of my resistance, dR, when I have a mechanical advantage of 1. When I have a mechanical advantage of less than 1, the distance of my effort is much smaller than the distance of my resistance, dR. And then finally, when my mechanical advantage is greater than 1, the distance of my effort is much greater than the distance of my resistance. The second class lever places the resistance force or load between the fulcrum and the effort force. In this type of lever, the resistance force and effort force are in opposing directions, and the direction of force does not change. The second class lever always has a mechanical advantage greater than 1. Examples include a wheelbarrow, nutcracker, or even a bottle opener. So again, looking at this picture here, you can tell that the distance of my effort is much greater than the distance of my resistance. Since there's a greater distance, we're going to have a mechanical advantage of greater than 1. In a third class lever, the fulcrum is located at one end of the lever with the effort force, my input force, between the fulcrum and the resistance force. In this type of lever, the resistance force and effort force are in opposing directions again. A third class lever does not change the direction of force, but it always produces a gain in speed and distance as well as a decrease in force. The third class lever always has a mechanical advantage of less than 1. Examples of this would include a human arm, catapult, or tweezers. So in the picture below, you can again see that the distance of my effort is much smaller than the distance of my resistance from the fulcrum or pivot point. So therefore, we'll have a mechanical advantage of less than 1. So I wrote this slide in a couple years ago when a student came up with a clever way to remember each class of lever. So for a first class lever, the fulcrum's in the middle. In a second class lever, the resistance is in the middle. In a third class lever, your effort force is always in the middle. So FRE 1, 2, 3. When you apply a force to a lever turning on a fulcrum, the turning effect of a force about a point is equal to the magnitude of the force times the perpendicular distance from the point to the line of action from the force. We refer to this as a moment. To calculate a moment, it's simply force times perpendicular distance. So again, when you apply a force, it's going to cause a rotation. That rotation or turning effect is considered a moment. And the force that produces or tends to produce that rotation or torsion is considered torque. The terms moment and torque are synonymous with each other. Consider this example of a lever moment calculation. In this picture above, it says calculate the effort moment acting on the lever. As a reminder, to calculate a moment, it's force times perpendicular distance. Do not get this calculation confused with work. Work, remember, is force times parallel distance. This is force times perpendicular distance. So the effort moment is going to be my force of 15 pounds times 5.5 inches. My effort moment is then considered to be 82.5 inches pounds. When a load is applied to one end of a lever, and we want to figure out how much effort force is going to be needed to counteract that resistance force, we're going to be looking at something called rotational or static equilibrium. When the sum of all my moments of a lever are equivalent to 0, the lever is considered to be in rotational or static equilibrium. The formal definition of rotational or static equilibrium is when the state in which the sum of all the clockwise moments equals the sum of all the counterclockwise moments about a pivot point. This would imply a condition where there are no external forces acting upon a particle or rigid body, and the body remains at continued velocity or at rest. That would imply that there's no velocity changes or acceleration. Using what you know about rotational equilibrium, now you should be able to calculate the unknown distance from the fulcrum to the resistance force. So again, to consider rotational equilibrium or static equilibrium, our effort moments going counterclockwise has to be equivalent to any resistance moments going clockwise. So in this scenario, my effort force is 15 pounds. My effort distance is 5.5 inches. My resistance force is 36 2/3 pounds, but I do not know the distance of my resistance. So to set this up as an equation, I'm going to set 15 pounds times 5.5 inches, equivalent to 36 2/3 pounds, times the distance of my resistance. And then I can simply solve for dr, and I get 2.25 inches. When calculating the IMA of a lever, again, we're going to use distance of my effort divided by distance of my resistance. Both effort and resistance forces will travel in a circle if unopposed. You'll notice here with the effort, when I apply that force, it's going to rotate counterclockwise. When I apply my resistance force, or my load, it's going to travel the opposite direction, clockwise. The circumference is the distance around the perimeter of a circle. Recall that the circumference of a circle is 2 pi r. So the distance of my effort is equivalent to 2 pi times the effort arm length. The distance of my resistance is going to be 2 pi times the resistance arm length. If I go to calculate IMA, dE over dr, I'm going to see that it's going to essentially be the effort arm length divided by the resistance arm length. In order to calculate the actual mechanical advantage of a lever, we're going to use the ratio of applied resistance force to applied effort force, or simply FR over FE. What is the actual mechanical advantage of the lever above? Well, we have 32 pounds of resistance, that's my FR, 16 pounds of effort, that's my FE. So using our formula, we get 32 pounds divided by 16 pounds. And again, the units should cancel as mechanical advantage is unitless. So we would say that this actual mechanical advantage is 2 to 1. If I asked you to calculate the ideal mechanical advantage of the lever above, we would use distance of effort divided by the distance of my resistance. So the distance of my effort is 5.5 inches. The distance of my resistance is 2.25 inches. If we divide those, again, the inches cancel out, and we get an ideal mechanical advantage of 2.44. Now consider this. Why is the ideal mechanical advantage always going to be larger than the actual mechanical advantage? Hopefully you understand from our lesson today that the reason why ideal mechanical advantage is larger than the actual mechanical advantage is because ideal mechanical advantage does not take into account friction. We're always going to have to use a little bit more effort in actual mechanical advantage to overcome that resistance of friction. When looking at the efficiency of a machine, the ratio of useful energy output to the total energy input, or the percentage of the work input that is converted to the work output. The ratio of AMA to IMA is going to help us determine its efficiency. To calculate efficiency in terms of a percentage, we're going to use the formula AMA divided by IMA times 100. So what is the efficiency of the lever on the previous slide? Well, we saw on the last slide that the AMA was 2, the IMA was 2.44. So to calculate the percentage of efficiency for that machine, we're going to take 2 divided by 2.44 times it by 100, and we get essentially 82%. No machine is ever going to be 100% efficient. So consider why. Again, it's due to friction and other energy losses that will cause machines to have less than the expected output. A wheel is a lever arm fixed to a shaft called an axle. The very center acts as the fulcrum. The wheel and axle rotate together as a simple lever to lift or move a load. The effort force can be applied to either the wheel or the axle and transfers a rotational force from one to the other. It is important to know which component, the wheel or axle, the effort force is applied. What's the trade-off? Different size wheels are helpful for different situations. Given the same input force, smaller wheels will have more output force, but will travel a smaller distance, while bigger wheels will have less output force, but will travel a greater distance. As you can see on this slide, to calculate the IMA of a wheel and axle, again, we'll be using the formula dE over dr. Both effort and resistance forces will travel in a circle if unopposed, similar to the slide that we saw with calculating the ideal mechanical advantage of a lever. So to calculate IMA of a wheel and axle, it's going to be our effort diameter divided by our resistance diameter. Or you could simply look at this as the effort of my radius divided by the resistance radius. What is the IMA of the wheel if the axle is driving the wheel? So if the axle is driving the wheel, that means our axle is our effort, our wheel is our resistance. So to calculate IMA, we'll use dE over dr, or 6 inches divided by 20 inches in this case, or a mechanical advantage, ideal mechanical advantage of 0.3. What is the ideal mechanical advantage of the wheel if the wheel is driving the axle? So in the second scenario, the wheel is the effort and the axle is my resistance. So again, using dE over dr, we get 20 over 6, or approximately 3.33 ideal mechanical advantage. When calculating the AMA of a wheel and axle, again, we'll use force of my resistance divided by force of my effort, FR over FE. What is the actual mechanical advantage if the wheel is driving the axle? So if the wheel is the effort and the axle is the resistance, I have 200 pounds of force being applied at the axle divided by 70 pounds of force at the wheel, which gives us an actual mechanical advantage of 2.86. What's the efficiency of the wheel and axle assembly? So again, to calculate efficiency, it's going to be AMA over IMA times it by 100. So 2.86 divided by 3.33 times it by 100, and we get an efficiency of the wheel and axle assembly of 85.9%. And our last simple machine that we'll talk about today is the pulley. A pulley is a wheel with a groove in its rim that is used to change the direction and or magnitude of a force exerted by a rope or cable. A pulley can make it easier to lift something heavy with a small force applied over a long distance of rope. There are two types of pulleys, fixed, shown in figure 1, and movable, shown in figure 2. A fixed pulley has an axle attached to a supporting structure that does not translate and changes the direction of a force. A movable pulley has an axle and a movable block and is supported by two parts of the same rope. A movable pulley can translate and move the rope when it is pulled. Pulleys are usually used in combination, as you see in figure 3. This is known as a block and tackle system, designed to reduce the amount of force needed to lift a load. However, the same amount of work is necessary for the load to reach the same height as it would without any pulleys. If a pulley system reduces the magnitude of an effort force, the effort force must act through a greater distance. The IMA of a pulley is equivalent to counting the number of strands opposing the force of the load. The method for calculating IMA formula is only true if the strands are opposite and parallel to the resistance force. So you'll notice in the first picture on the top right, this is a fixed pulley. It has an ideal mechanical advantage of 1, and it changes the direction of force. So if I have a 10-pound load and I'm using this pulley system and it has an ideal mechanical advantage of 1, it's going to require 10 pounds of effort to move that load. In the other picture, we have a movable pulley. This is considered a second-class lever with an IMA of 2. The force directions stay constant. So I have 10 pounds of force, that's my load. Since this has an IMA of 2, it's only going to require me to use half the effort. So in this case, 5 pounds of force. When fixed and movable pulleys are used in combination, again, this is referred to as a block and tackle system, it provides a mechanical advantage and change of direction for effort force. Note, if a single rope or cable is threaded multiple times through a system of pulleys, you can find the ideal mechanical advantage of the pulley by counting the number of strands opposing the force of the load. So in this case, our load is a 600-pound motorcycle. The load is going down. If I count the number of strands opposing that load, I have 1, 2, 3, 4. I can't count this last one because this strand is going in the same direction as the load. So we would say, based off this scenario, the IMA of the pulley system is 4. If more than one simple machine is used in tandem together, this is referred to as a compound machine. If one simple machine is used one after another, the mechanical advantages are multiplied together. So in this scenario, we have several different simple machines. We have a movable pulley system as well as a lever. So to calculate the ideal mechanical advantage of this total compound machine, we're going to take the IMA of the pulley multiplied by the IMA of the lever. So again, the IMA of the pulley, you're going to count the number of strands opposing the load. It says here that my load is going down. So I have 2 strands that are opposing it. So we have an IMA of 2 for the pulley. In terms of the IMA of the lever, we're going to use that formula distance of my effort, dE, divided by distance of my resistance, dr. So in this particular example, the distance of my effort of the lever, dE, is 12 feet. The distance of my resistance, dr, is 4 feet. So if I multiply those two ideal mechanical advantages together, 2 times 12 over 4, I get 6 as my ideal mechanical advantage of this compound machine. It's also important to understand that when pulleys are used in combination with separate ropes or cables, the output of one pulley system can become the input of another pulley system. Again, this is referred to as a compound machine. It's asking in this example, what is the ideal mechanical advantage of this pulley system? So what we're going to do is take the ideal mechanical advantage of each of these individual pulley systems and multiply them together. Notice all 3 of these pulley systems are movable pulleys. So we have an ideal mechanical advantage of 2, another ideal mechanical advantage of 2, as well as goes for the third one. So if I multiply those all together, 2 times 2 times 2, the total ideal mechanical advantage of this pulley in combination is 8. And to calculate the actual mechanical advantage of a pulley, we'll use FR over FE again. So in this example, it's asking us to calculate the AMA for the pulley system to the right. Our FR, our force of our resistance, is 800 pounds. The force of my effort being applied is 230 pounds. If I divide those two, the pounds cancel out and we get an actual mechanical advantage of 3.48. In terms of efficiency for the system, AMA divided by IMA times it by 100 gives us approximately 87% efficiency. And I just wanted to address a couple of misconceptions that often come up with simple machines. The first one deals with the pulley system. In the pulley on the right, this does not have a mechanical advantage of 2. Although the vertical forces from the 2 strands are each half of the resistance force, the tension in the string depends on the angle. We will not address these types of problems here because we would have to use some trigonometry, though you will learn how to do it in Unit 2 when we get to our civil engineering section with trusses. In your measurements, keep the strands in the opposite direction from the resistance force to avoid this complication. Another common misconception is that when you are looking at a pulley system, you simply just count the number of effort strands that are being pulled up. That only sometimes works. Consider this example. In the movable pulley here, the effort force is used to pull the pulley down along the load. This is used, for example, in pulling the foot of a sail downward after it has been hoisted. The resistance will only be forced downward 1 foot for every 2 feet of rope pulled out of the system. So again, if you notice, I have a resistance force of 80 pounds of force. So I have an IMA of 2 because there's 2 strands opposing that force parallel in opposite direction. So we cut our effort force in half to 40 pounds of force applied.